Myself, Prabha Anjay, working as a assistant professor in EC department at SNS College of Technology. In this lecture video, I am going to discuss about the linear phase FIR filter from Unit 3, that is FIR filter design. Let us discuss. Yeah, we know the what is FIR filter. FIR filter, unit sample response or impulse response H of n has finite number of terms. FIR filters, the filters designed by considering all the finite samples and impulse response. The specification of a digital filter will be desired frequency response HD of e power j omega. The desired impulse response HD of n of the filter can be obtained by taking IFT, that is inverse Fourier transform of HD of e power j omega. The HD of n will be an infinite duration discrete time signal defined for all values of n small n in the range of minus infinite to plus infinite. The transfer function h of z of the digital filter is obtained by taking z transform of impulse response. Since hd of n is an infinite duration signal, the transfer function obtained from hd of n will have infinite terms which cannot be realized or implemented in a digital system. Therefore, finite number of samples hd of n are selected to form the impulse response h of n of the filter. The transfer function h of z is obtained by taking z transform of finite sample impulse response h of n. The filter designed by using finite samples of impulse response are called finite impulse response filter. Yeah, here we can say what are the advantages and disadvantages of FIR filter. Yeah, advantages of FIR filter, that is exactly linear space can be easily designed. Efficient realization of FIR filter exists as both recursive and non-recursive structure. FIR filter realized non-recursively by direct convolution are always stable. Round of noise, which is inherent in realization with finite precision arithmetic, can easily be made small of non-recursive realization of FIR filter. Disadvantages of FIR filter is the duration of the impulse response should be large to adequately approximate sharp cutoff filter. Hence, a large amount of processing is required to realize such filter when realized via slow convolution. The delay of linear phase FIR filter need not always be an integer number of samples. This non-integral delay can lead the problem in signal processing applications. Okay. Here we can see the steps in designing FIR filter. First step is choose an ideal frequency response, that is HD of e power j omega from the given specification. And second step is take inverse discrete Fourier transform, because frequency domain to time domain conversion we are for frequency to time domain conversion we are applying inverse Fourier transform. Take inverse Fourier transform of hd of e power j omega to get small hd of n, or to get small hd of n. If hd of n is determined, then convert the infinite duration hd of n to finite duration h of n. Or if h of k determined, then take n point inverse dft to get h of n. Take z transform of h of n to get h of z, where h of z is the transfer function of the digital filter. Choose a suitable structure and realize the filter. Verify the design. In order to verify the design, determine the actual frequency response h of e power j omega of the filter by letting z equal to e power j omega in h of z, and sketch the magnitude response of h of e power j omega. These all are the steps in designing FIR filter. Okay, the frequency response h of e power j omega is complex quantity. H of e power j omega we can write the magnitude response as well as phase response. The magnitude of frequency response is constant and phase is a linear function of frequency. If the function of frequency response of a filter is linear function of frequency, then the filter is called linear phase FIR filter. In order to examine the linear and nonlinear phase characteristics, two delay functions are defined and they are phase delay and group delay. Phase delay is represented as tau p, which is equal to the minus theta of omega divided by omega. For group delay is represented as tau g equal to minus d power d omega into theta of omega. For linear phase FIR filter, linear phase FIR symmetric filter, both group delay and phase delay are constant. The filter are classified according to their frequency response characteristics. The ideal frequency response HD of e power j omega of four major types. They are low pass filter, high pass filter, band pass filter, and band limit filter. Here you can see the ideal frequency response of linear phase FIR filter. These all are the ideal frequency response. Higher frequency responsible for the band pass filter and band stop filter. This is the ideal magnitude response of the low pass filter, high pass filter, band pass filter, band limit filter. This is band pass filter and band limit filter. Band limit filter or a band stop filter, both are same. This is the magnitude response of a practical low pass filter. The transition of the frequency response from passband to stop band defines the transition band or transition region. The passband frequency omega p defines the edge of the passband, while the stop band frequency omega s denotes the beginning of the stop band frequency. And del p passband, del p is represented as passband ripple, del s is represented as stop band ripple, and also omega p is a digital passband frequency, omega s is digital stop band frequencies. And some characteristics of FIR filter. Since h of e power j omega is complex, it can be expressed as amplitude function, magnitude function, and phase function. H of e power j omega equal to plus or minus magnitude of h of e power j omega and angle of the filter. And here a of omega is nothing but the amplitude function of the h of e power j omega, and phase function of the h of e power j omega is theta of omega, and magnitude function is represented magnitude of h of e power j omega. When h of n is real, the magnitude function is a symmetric function and the phase function is an asymmetric function. Okay. If you have any doubt, you can ask me through comment. We will meet in next video. Thank you.